Hello everyone, welcome back. So, today we are going to learn how to solve forced vibration case. So, we have the SDOF system that we solved for the homogeneous case. So, there is a spring and it is attached to a mass of say m, and then there is a damper. So, the spring constant is k and the damping constant is c and the mass is represented by m. So, the degrees of freedom in this case we have x of t and we have also a forcing function f of t. Now, the governing equation of motion in this case is mx double dot plus cx dot plus kx is equal to f of t. Obviously, this is an initial condition defined at t equal to 0. So, x 0 is x naught and the velocity that is x dot at t equal to 0 is also defined. So, these are the two initial conditions. Now, that is the problem statement. So, today we are going to solve this equation for forcing function f of t. Now, we have already solved the homogeneous part, that means the total solution x of t, it has two components x of t that is the complementary function plus x of t that is particular integral. Now, this complementary function we have already solved when we have the right hand side equal to 0 and we apply the initial conditions. Today, our task is to solve this particular integral. Now, before we do that, if you recall, what is the first part x t of Cf, if you recall it is e to the power minus eta omega n t c cos omega dt plus d sin omega dt. So, that is the solution we derived earlier, and there are two constants c and d and that we evaluate from the initial condition. So, that is what we have already solved. So, today our first task is if we define this f of t as say f naught, a constant. That means, if I draw the schematic diagram, so we have time t, as time progresses we have a forcing function which is constant, that is f naught. So, this is our f of t. Now, before we solve the equation that is governing equation of motion, we can intuitively conclude the nature of this solution. Because we have a linear system and we have a constant forcing function, just imagine if we have a portal frame which actually we idealize by this SDOF system and we apply a forcing function which is say f naught, then what will happen? This portal frame will actually deform in this direction. So, this there will be a deformation, and because this f naught is constant for all the time, obviously what will happen, there is no chance that system will come back, but there will be a permanent deformation, and this deformation also we can quantify if this is delta. So, delta is equal to the force that we apply divided by the stiffness, the lateral stiffness of the system provided by the two columns that we can see in this portal frame. Obviously, the solution will be same for this SDOF system also. So, if we apply this f naught, which is in this case constant, obviously the response which we will get is also constant. And if that is the case, If x of t it is constant, obviously if we differentiate that function we will get 0. So, the velocity and acceleration component due to this forcing function will be 0, because this forcing function, if not, it does not change with time, it is a constant force. So, obviously the particular integral in this case will be equal to what? The force that we apply divided by the lateral stiffness of the system. And if we combine these two, we basically get the total response or total solution. So, in this case it will be x of t is equal to e to the power minus eta omega n t. I do not write the details of this third bracketed term, which is already there, plus then f naught divided by k. So, we have the total response due to a constant force. Now, our next task obviously is to find out the two constants c and d, and here I just draw your attention that whenever we have a forcing function, then first our task is to find out the total solution, and then once we find out the total solution, then using this total solution, the closed form expression that we get here. So, this expression we have to use to satisfy the initial conditions. And that is the difference between what we did earlier, because in the earlier case, because of the 0 right hand side, we had only the first part. So, this part was there, and we evaluated c and d based on the first part only. But here that is not the case, we have to consider the complete expression, and then we have to satisfy the initial condition. So, if I differentiate this expression, what we will get? So, minus eta omega n e to the power minus eta omega n t, then the third bracketed term which I am not writing for the moment, plus e to the power minus eta omega n t. Then within the third bracket we have the first term, that is minus c omega d sin omega dt plus d omega d cos omega dt. And if we differentiate this second term, obviously that will be equal to 0. Now, what we have to do now? We have to satisfy the initial condition. So, if we consider the first initial condition, so x 0 is equal to x naught. If that is the case, obviously x naught is equal to, we have to put 0 in this expression. So, if I put t equal to 0, obviously e to the power minus eta omega n times 0. So, that will be e to the power 0. So, that is 1. Then within bracket we have c times cos omega dt times 0. So, that term will be there, c, and then plus d times sin of omega dt at t equal to 0. So, this will be 0, which is multiplied by 1, then plus we have f naught by k. So, if we just remove this part, so what we have c plus f naught by k. So, let me write it once more. So, what we have here c plus f naught by k. That means what we get? We get c is equal to x naught minus f naught by k. So, that is the first condition we apply, and we get first constant, that is c. Now, if we apply the second condition, that means velocity at t equal to 0, which is x naught dot, then we have the velocity x naught dot is equal to again minus eta omega n times 1 times the third bracketed term. That means, we will have C plus d equal d times 0. So, we do not write that part, plus e to the power minus eta omega n times 0. So, this is 1, and here what we have is minus C times omega d sin omega dt 0. So, that first part is 0 plus d omega d times 1, because cos omega dt at t equal to 0 is 1. So, what ultimately we get is x naught dot is equal to minus eta omega n times C. For C, we can write down x naught minus f naught by k plus d omega d. So, then what we get is d equal to 1 by omega d, and then we have x naught dot plus eta omega n times x naught minus f naught by k. So, what we have? We have both C and D, and for that we use the two initial conditions. So, we have solved both C and D, and then definitely we can write down the total response. So, in this case, total response, if I write down, will be what? E to the power minus eta omega n t C cos omega dt plus d sin omega dt plus f naught by k. So, what is C? C is equal to x naught minus f naught by k, and d is equal to 1 by omega d, and then we have x naught dot plus eta omega n within bracket x naught minus f naught by k. So, that is the complete solution when we have a forcing function which is constant. So, that was the forcing function f naught for all time. So, this is the forcing function, and if I draw qualitatively the response of the structure. So, we have T, and then in y axis we have the response of the structure. So, what is f naught by k? We call it, say, x s t, that is the static response. So, if this is the, say, static response, then what will happen? At t equal to 0, we have some displacement, that is x naught. So, it starts from x naught, and then so, this is the initial displacement is x naught, and we can also draw the velocity here depending upon the slope at this point t equal to 0. So, initially it starts the vibration, that is the complementary part, complementary function, and then as time progresses, because of damping, then the initial transients actually dies down, and then ultimately the response is equal to the static response x s t, which is equal to f naught by k. So, This is the nature of solution we get when we have the forcing function which is constant. Now, obviously, depending upon the values f naught and then x naught and x naught dot, the slope may be going upward, or if x naught dot equal to 0, then the slope at this t equal to 0 is horizontal. So, depending upon the values of these conditions x naught dot and the forcing function, the displacement may be positive or negative, but qualitatively this will be the nature of the total response when we have forcing function which is constant. So, at the end of this module, we will have a session where we will solve some example, and there we will use MATLAB, and using MATLAB we will solve this and we will also plot this. And once we develop a code for different values of initial conditions, we can plot and study the nature of the solution. But in every case we will see the vibration will start with some initial transients because of the initial conditions, and then as time progresses, then it becomes the static response, and this part onward where it becomes constant, actually it will oscillate and then ultimately it becomes constant. This part is called, so after certain time, so this part of the response is called the steady state response. And so this is the steady state response, and the response before that is what is called transient response. So, initially the transient response dominates, but because of the damping, the system, it gradually loses that energy and then ultimately it reaches the steady state. So, that is the nature when we have a constant forcing function. Now, our next case is when we have forced vibration with harmonic excitation. So, what we have mx double dot plus cx dot plus kx is equal to f of t, and there are initial conditions. But in this case, what we have, f of t is equal to the harmonic excitation. So, we have some f naught, that is the amplitude of the harmonic excitation, and we have sin lambda t. So, lambda in this case is the forcing frequency. Now, so if we consider the governing equation of motion, and then if we divide both sides of this equation using the mass m. So, what we have c by m in the second term, x dot plus k by m in the third term times x is equal to f naught by m sin lambda t. Now, if you recall, what is c? C is equal to twice eta m omega n, and then what is omega n square? This is equal to k by m. Obviously, we can further simplify this equation. We have x double dot plus twice eta omega n x dot plus omega n square x is equal to f naught by m sin lambda t. So, this is the equation we are going to solve and find out the total response of the system. Now, obviously, if we have a linear system and if we excite the linear system with a harmonic force, a sinusoidal force, obviously the output will also be sinusoidal. So, we can propose a trial solution x of t is equal to a cos lambda t plus b sin lambda t. Obviously, x dot of t will be what? Minus a lambda sin lambda t plus b lambda cos lambda t, and then x double dot of t is equal to minus a lambda square cos lambda t minus b lambda square sin lambda t. Now, we can substitute these expressions in the original equation. So, what we get is, in place of x double dot, we write minus a lambda square cos lambda t minus b lambda square sin lambda t. Then the next term will be plus twice eta omega n, and then for x dot we have minus a lambda sin lambda t plus b lambda cos lambda t, and then for the third term we have omega n square. For x we have a cos lambda t plus b sin lambda t. So, which is equal to f naught by m sin lambda t. Okay. So, now we have on the right hand side we have f naught by m times sin lambda t, but on the left hand side what we have? We have if you see this expression different combinations of cos lambda t and sin lambda t. So, what we can do effectively, we can collect all the terms for cos lambda t and similarly sin lambda t, and then we can simplify this expression. So, what we can do if we continue here. So, we have, so the first term minus a lambda square cos lambda t. So, let us collect all the terms for cos lambda t. So, the next term is twice eta omega n times b lambda, and then plus omega n square times a. So, this multiplied by cos lambda t. Similarly, we can also collect all the terms, all the coefficients of sin lambda t and then simplify. So, let us do that. So, we have minus b lambda square and then minus twice eta omega n a lambda, and then we have plus omega n square b times sin lambda t. And on the right hand side we have f naught by m sin lambda t. So, what we have, if we look at this expression, on the left hand side we have cos lambda t multiplied by this third bracketed term plus sin lambda t, which is also multiplied by this third bracketed term, you can see on your screen. While on the right hand side we have f naught by m times sin lambda t. Now, if we compare these two, the left hand and right hand, what we can easily conclude, the coefficient of cos lambda t must be equal to 0. So, we have minus a lambda square plus twice b eta omega n lambda plus a omega n square, this is equal to 0, and the coefficient of the sin lambda t in the left hand side must be equal to f naught by m. So, what we have, minus b lambda square minus twice a eta omega n lambda plus b omega n square, this is equal to f naught by m. So, we have two equations. Now, obviously, we can further simplify this equation. So, if I simplify the first equation, what we have omega n square minus lambda square times a plus twice eta omega n lambda times b is equal to 0. Similarly, if we consider the second expression, so what we have, if we simplify, we have minus twice eta omega n lambda times a plus, there will be omega n here. So, omega n square minus lambda square times b equal to 0. So, we have two equations and there are two unknowns. So, what are the two unknowns? We can easily identify a and b. So, we have to solve these two equations to find out what is a and b. That we will do in a minute. So, let us solve these two equations. Let me write it once more. So, we have first equation omega n square minus lambda square times a plus twice eta omega n lambda b is equal to 0, and then minus twice eta omega n times lambda times a plus omega n square minus lambda square times b, which is equal to, just let me check what we wrote in the previous expression. I think there is a correction here. So, it should be f naught by m, small correction. So, we have here f naught divided by m. So, that is the first equation and this is the second equation. Now, obviously, all of you can solve this. I leave it as an exercise. I just write the solution for a and b, that you can easily do it, cross verify at your end. So, what we have, minus twice eta omega n times lambda divided by omega n square minus lambda square plus lambda square whole square plus twice eta omega n lambda whole square and whole multiplied by f naught by m. So, that is the first constant A, and the second one B is equal to omega n square minus lambda square divided by omega n square minus lambda square whole square plus twice eta omega n lambda whole square times f naught by m. So, I leave it as an exercise, all of you please check it at your end, and if you have any trouble, then we can solve this when we will have our interaction session. Otherwise, it is very simple, two unknowns and two equations, we can easily solve it. Now, what we can do once we have A and B, then we can write down the complete solution. So, what is the complete solution? Again, if I write down the x of t, we will have e to the power minus eta omega n t and then c cos omega dt plus d sin omega dt, plus obviously we will have the solution due to forcing function. Recall what was the solution? If we go back to the previous case, so our proposed solution is this one, x of t is equal to a cos lambda t plus b sin lambda t, and we have already found out the expression for a and b. So, it will be a cos lambda t plus b sin lambda t, and the second term is, so this second term is particular integral, and this first term what we have is the complementary function, and we have the expression for A and B. Again, remember, when we have to find out the constants, that means C and D, because A and B we have already found out, you have the expression here, but to find out C and D we have to satisfy the initial conditions, and then in this case again we have to consider the complete expression when we obtain the expressions for C and D. So, for that we have to satisfy the initial conditions, that we will do in a minute, but before we do that we can actually simplify the expression what we have here. So, for that what we do, we can consider omega n square minus lambda square is equal to cos of theta and then twice eta omega n lambda is equal to sin theta. Now, if we do that, then we can further simplify the particular integral. So, that we will do, but before we simplify this expression, let us first qualitatively plot the response and then we will see how does it look like, and then we will move further, we will solve this C and D, we will see their expressions, and we will also simplify this expression for total solution. Now, just by looking at this total solution, what we can conclude, it has two parts. First part, complementary function, again that is the transient part, and in this part what we have exponentially decaying sinusoid. That means as time progresses, because of the presence of damping, this vibration will come to 0, but we have another component in this case which is a sinusoid. So, obviously what will happen, it will continue vibrating the forcing function which is p sin f sin lambda t. So, that means the forcing frequency in this case is lambda. So, what we have, we have this envelope, that is e to the power minus eta omega n t, and then within that we have the initial vibration. So, after certain time, then what will happen? It will continue vibrating with the same frequency. Earlier case, this function used to go down when we had the homogeneous part only, that means free vibration. So, it will gradually go down, but because we have a forcing function which is in this case sinusoid. So, once the transient part dies down, then it will keep on vibrating with the forcing frequency, and it will continue ever with that vibration. So, obviously we have again after certain point, when this transient part will die down, we have the steady state response. So, we have initially transient, actually we have the total solution which is the summation of transient and steady state, but in the initial part the transient dominates, and because of the damping it gradually goes to 0, leaving behind only the steady state response. So, with that let us close here. In our next class, what we will do, we will simplify this expression for the total solution, and we will see what is the fundamental nature of the response when we drive a linear system with a harmonic frequency. In this case, the harmonic frequency is lambda. So, if we drive that, what is the nature of the solution? Intuitively, we have already drawn what should be the nature. So, that is the initial displacement, and this is the initial velocity. So, the nature of total response we have already studied, but we will further simplify this expression, because that will give us a better insight of the nature of the solution that we get from this expression. So, let us close here. We will continue in our next class. Thank you very much.